In this Digilock tutorial, we will introduce you to simple locking techniques using the PID module and lock a laser to an atomic reference. To take full advantage of this video, you should be familiar with operating your laser and have a basic understanding of active frequency stabilization and the operating principles of a PID regulator. First, let us have a look at the system setup. A DL Pro laser is fiber connected to a Doppler-free cesium spectroscopy setup. The Doppler-free absorption signal from a compact spectroscopy, COSY, is fed into the main Digilock input. Additionally, the Doppler broaden signal is fed into the auxiliary input. The Digilock is connected to a scan control unit via an internal backplane connection in a DC 110 supply rack. The scan control will act only as a voltage amplifier to supply the PCT inside the laser head. The internal scan generator has been disabled by setting the trigger switch to external. For this first locking tutorial, no other connections between the Digilock and the laser head are needed. Current, temperature and the scan parameters of the Digilock have been set so that both fine transitions of the cesium D2 line are clearly visible. To keep things simple, we will first lock to the side of a Doppler broadened peak. This carries the advantage of the slopes being not as steep, making the adjustment of the locking parameters less critical. Instead, we can focus on the interplay between the various user interface elements. In order to bridge the gap between the traditional analog scanning and locking modules, we will try a pedestrian's approach first, which means that we will control the laser in a fashion that resembles the behavior of the analog modules. It will also emphasize the elegance of the autolock method that will be covered later. In order to do that, I will make sure that both the scan and the offset module will send their respective signals to the scan control. Now we need to select the feature to which we want to lock the laser, so we need to zoom in onto it. With a normal scan control, one would gradually reduce the scan amplitude, adjust the offset, reduce the amplitude again, and so on. So let us do that. I will use the arrow keys on my keyboard to adjust these parameters. As you notice, I have to switch between amplitude and offset a few times. Next, let us have a look at the PID controller. The PID section consists of 4 different tabs. The first one deals with the autolock function. We are not going to use it for now, so we need to make sure that it is not activated. So I uncheck the box. The last tab is for advanced purposes. We can just ignore it for now. What is left are 2 PID tabs corresponding to 2 separate PID regulators. Having 2 regulators will enable you to do advanced locking by assigning each PID to a different bandwidth domain. For now, we are going to use only PID 2. If you have followed the introduction to the graphical user interface, you already know that the Digilock frees you from physically rewiring modules. Instead, the different functions inside the Digilock can be wired virtually. We are going to do just that by defining the input signal the PID should be locking to. Since our Doppler broaden signal is fed into the auxiliary port, we select that one. Next, we have to tell the Digilock where to send the regulator signal to. Since we are only using the PCT for wavelength tuning, we have to send the output to the scan control. Now, we need to determine the signal level to which we want to stabilize the laser. This value will define the set point of the PID that is set in the General tab at the bottom of the virtual PID module. We can now make use of the trace cursor that we already touched upon during the introduction. In the lower right of the oscilloscope section, I right-click on this cursor icon and define Snap to Oscilloscope Channel 2, since the spectroscopy signal is displayed in Channel 2. I now grab the vertical line of the crosshair and drag it horizontally until I reach the point that I would like to lock to. In the lower right, I can now read off the voltage level and enter this value in the setpoint field. Next, we disable the autoscale feature. We will need this in the next step to manually fine-tune the laser wavelengths so that the input signal gets close to our setpoint. Seeing the changes is easier with a fixed scale. So let us enter reasonable values to define the display range. To fine-tune the laser, I switch off the scan. As a result, the signal will become a DC voltage level. Now I place the cursor in the 100 mV range of the offset value and fine-tune the laser using the up and down arrow keys. You can see that the signal level changes accordingly. I repeat this until the signal level gets near my set point. Before I lock, I need to make sure that the slope is set correctly. In our case, I want to lock to the positive slope of the fringe, so I will adjust my switch accordingly. Last but not least, we need to take care of the PID locking parameters. It is recommended to keep the values for the overall gain and the integral part quite low in the beginning. The P and D contribution are set to 0. Setting the overall gain and I to 10 will provide us with sufficient feedback to establish a basic lock. Once the lock is established, we can return to these values and optimize them. We are now ready to engage the lock button. And behold, the DC offset value changes to our set point. Congratulations! We have just mastered our first attempt at locking the laser. We can now begin to optimize the locking parameters. For that, I will place the cursor before the highest digit in the field of the I value. I press the arrow up key and increase the value. You will notice that the cursor remains in front of the highest digit, even if I cross from 9 to 10 or from 90 to 100. This allows me to quickly scale the parameters and determine the order of magnitude. As soon as the value gets too high, the feedback loop will self-oscillate. At this point, I switch to the next lower digit and decrease the gain until the oscillation stops. The overall gain and the individual values for P, I and D are multiplied, which means that increasing the overall gain by a factor of 10 would mean that I have to decrease the individual parameters by the same factor. Let me quickly adjust the other parameters as well. We finally end up with a quite stable lock. The Digilock, however, is capable of more than that. The auto-lock feature will take away a lot of the work from us and make locking much more intuitive. So let's go ahead and try it out. Let me quickly bring the system back to its original state. I will adjust the scan amplitude and the offset so that all the fine transitions are visible. Now we need to enable auto-lock, so I select the auto-lock tab and check the mark. Once enabled, the auto-lock will override certain settings of the individual locking modules. One of them is the input signal. It is currently set to main in. If I quickly switch to PID2, I notice that the PID2 input is main in as well. Remember, a few minutes ago we have set that to auxiliary in. So we need to switch back to the auto-lock tab and define auxiliary in as the input. Then we have to define which regulators the auto-lock shall act on. We will use only PID2, so I leave the others unchecked. That is all for now. We will not need to worry about the settings in the General, Window and Relock tabs. We can leave the settings in the PID 2 tab unchanged. We are going to lock to the same feature and therefore have no reason to change the locking parameters for now. Next, we need to switch our display mode to auto lock. This will set the virtual oscilloscope into XY mode. There no longer is a time axis. Instead, the x-axis displays the scan signal. In auto lock display mode, we are able to interactively tune our laser. Let us start with shifting the spectroscopy signature to the right. Before I do that, let us note the actual set point value. I select the hand tool and drag the signal to the right. If we want to zoom into our feature, we no longer need to make adjustments to the scan amplitude. Instead, we can use one of the zoom tools. I personally prefer the horizontal window tool, so I select it and then drag across the part of the spectrum I would like to have displayed. Now I need to define the locking point and therefore select the crosshair tool. I drag across the feature to the point of interest. Then I right-click and select PID Lock to Slope. The original curve turns blue. At the same time, I can observe the software tracing the curve and stopping at the lock point and enable the lock. If I want to unlock, just right-click into the scope's main window and select one of the two unlock options. That's all. Easy and intuitive, isn't it? In another tutorial, we will look into advanced locking techniques like top of fringe locking and making use of both PIDs.